Good afternoon. I'm Muhammad Nizami. I currently work at Finaco Ltd, but for this presentation, I'm presenting my research with my supervisor at Institute Technology Bandung, School of Electrical Engineering and Informatics. Our work is decision tree neural parametric violin synthesizer. First, introduction to our research problem. So, musical synthesis is the work of creating audio from musical sheets automatically. This allows to create musical audio without using human performer, so it is usually cheaper to use synthesizers. There are two ways of synthesizing musical audio. First is non-expressive, and the second one is expressive. In non-expressive audio, there are no variations in dynamics, timing, and etc. And in expressive audio, there are variations in dynamics, timing, and pitch deviations from the written score. So if we hear, this is an example of expressive audio. And this is the non-expressive audio. Okay. And this is an example of expressive audio. So in expressive audio, we hear variations and more human, and it is usually more preferred than non-expressive audio, especially in some genres like classical music. For other instruments like piano, there are already working and good expressive synthesizers. But for both string instruments like violin, there are not yet a fully automated expressive musical synthesizer, only separate components. This is because for violin, we have continuous excitation and more various timbre, more various expressive gestures. So previous researches only for expressive both string instrument synthesis only in separate components, like producing sound from musical sheets and gesture plane. There are many here, and then there are also from musical sheet it produces gesture plane. So there are no complete end-to-end from musical sheet to expressive sound. These components, if we see the inputs and outputs, we cannot combine them together because they are incompatible. The gesture planes and expression planes are different in each of these components. So our research goal is to provide fully automated expressive violin synthesis method. However, from previous researches, the existing components cannot be combined together because they are incompatible. And if we want to complete one of the components by adding the missing component, we have data collection problem, mainly errors from annotations, and it is not cheap to annotate data manually. So our proposed solution is to adapt a singing synthesizer, neural parametric singing synthesizer, which has already done sound musical sheet to sound fully automated. They have similarities. Firstly, they are both continuous excitation with continuous expressive gestures with various timbre, various dynamics, and they are continuous. And both singing and violin, both singing and both string instruments are mostly monophonic. Here is the neural parametric singing synthesizer. So the concept is to encode the audio using vocoder. We have fundamental frequency, voice on voice, spectral, and this one I forgot what it is. Basically, the audio is encoded into parameters, which is then used to train the models, the neural network models. So the neural network models only produce the parameters, and then the parameters is then synthesized using a vocoder. Synthesized the sound using vocoder. For the models, they use VoiceNet architecture. So the inputs are acoustic features and control features. This is from sheets and phonetic input, and the acoustic features are previous outputs from the model. The output is acoustic features in T+1, and then this is the loss function. So just some details. And for violin synthesizer, the modifications are: first, we use different encoder for the audio. So the previous one uses vocoder, which is specialized for voice, and this one we use harmonic and stochastic, which is more closely related with violin sound. So violin sound is more similar to harmonic waves and some stochastic components. And the second modification is that there are no phonetics inputs, because as we know, violin and other bowed string instruments doesn't have lyrics. And other modifications are in the model related with following the harmonic plus stochastic synthesis method. For timing model, we use decision tree because of bigger timing definitions range, and these are the features. For complete features, you can refer to the paper. And for pitch model, we use neural network. These are the outputs. And timbre model, these are the models for representing the timbre, for outputting the timbre representation. These are the features. You can refer to the paper for the complete features. And then let me show you the experiment results. This is the model preparation, and this is the first one, the quantitative one. So the correlation coefficients, mainly they are good, but we have some poor results here in the harmonic magnitude and stochastic envelope. For the whole system output, the correlation coefficient is better than baseline. So the baseline is the one without all these models. The input is just using RPM. So RPM is supposed to be inputted with musical sheet and gestures, expressive gestures, but we use flat expressive gestures here. So obviously the correlation will be close to 0 or even negative. For the neural parametric, our system, there are slight improvements in the correlation coefficient. The correlation coefficient is now positive. So for correlation coefficient, -1 is very bad, 1 is very good, 0 is there are no correlation. So we have positive correlation here. It is quite good, not quite good, but it is better than the baseline. The problem might be in the dynamics or the timbre or both. So we are going to test the hypothesis whether the problem is there. For next test, which is listening test, we use hybrid. So we use expressions from our model for dynamics and pitch deviations and timing. But for the timbre, we use RPM. So this is the naturalness preference test. So the listeners are given a set of pair of tracks, whether they are DTNP or hybrid, against baseline, but they don't know which track is which. They are randomized. So the DTNP, we have, so both DTNP and hybrid, we have low preference against RPM. But for hybrid, it has higher preference. So we have further confirmed our previous hypothesis, this hypothesis, that the system produces poor timbre. If we see their reasoning, the listener's considerations when they choose one track over the other, the left one shows that DTNP is more natural in terms of timing, fingering, phrasing, human fingering, rubato, trill, pitch transition, dynamics. So here, everything is more natural, except the mixing. Only a reduction in gain. This means that the timbre doesn't follow the decrescendo. And then the timbre does not show the pitch clearly. So all this, all these considerations, our system is poor in timbre in general. So the timbre is not clear, and that the timbre does not follow the expressive gestures. So these are our conclusions and future works, that our system is able to learn expressive patterns except the timbre. So the timbre is not realistic. By itself, in general, the timbre is not clear, and then in relation to other expressive gestures, they are not good. So for future work, it should focus on producing realistic timbre with our produced dynamics, pitch deviations, pitch variations, timing, etc. So these are the possible future works. Thank you for your attention and good afternoon.